Good morning. Oh wait. Okay, it may not be morning everywhere. So good morning, good afternoon, good evening, and good night. Wherever you are, it's good to have you here with me today. In this video, we'll be talking about the basic concepts, basically the fundamental concepts of simple harmonic motion before we go into the graphs, velocity, and more. So we're going to start with the fundamental concepts today. So as you can see, I have drawn springs attached to the wall. And I've drawn my equilibrium line here, as you can see. This is actually my load, or you want to call it mass, no problem. The second scenario is basically a scenario where I extend the mass, or basically I extend the spring, and 3 is basically like compressing it. Okay, so let's begin. So first things first, you have to know that based on Hooke's law, okay, we're going to use Hooke's law. Okay, let me change color. Wait, let's use black. Okay, Hooke's law. Okay, Hooke's law is F equals to negative kx. Why is that negative all of a sudden? Why? Okay, calm down, chill. I'll walk you through these scenarios and I'll tell you why the negative should be there and why it is very significant when it comes to simple harmonic motion. Okay, so let's get to it. Okay, we will start by labeling our diagrams. So in equilibrium, I'm going to label my length here as as x0. Okay, but we're not going to use that actually, but so okay. The second scenario, let's say I'm extending my spring with this load for, let's say I'm extending it for, let's say 10 meters. Okay, I'm extending it to the right for 10 meters. And for the scenario 3, I'm extending it to the left for 10 meters as well. Okay. Now I'm going to indicate my direction. So to the right is positive, to the left is negative. You can do it the other way around. To the right is negative, to the left is positive. No problem, as long as you're consistent with it throughout your calculation, then you'll be fine. Okay? So now, let's start with the second scenario. So in the second scenario, I have extended the spring for 10 meters to the right. So this is my equilibrium position. So anything to the right side of my equilibrium position, any length that I extend to the right side of my equilibrium position, doesn't matter how long or how short, as long as it is to the right of my equilibrium position, it will be positive. Okay? And if it's the left of my equilibrium position, it's negative. So I think it's better I just label this as negative and this is as positive. Okay, now let's say I were to use it as just F equals to kx. Okay, let's try and see what happens as we go along. So F equals to kx. Okay, I'm going to let my K be, for instance, 50 Newton per meter. So what is K? K is your spring constant. So let me just label here. K is your spring constant. So whether you extend a spring or you compress your spring constant remains the same, because spring constant actually relates to the stiffness of the spring and it is independent to the extension and compression, so it will not change. X is your extension length or your compression length, either one depending on the question you're looking at. Okay, now coming back, F equals to kx. Okay, so my K is 50, my X is 10. So my spring force will be 500 Newton. Now I want you to take a moment And think about it. I said my direction to the right is positive, and my force here is positive. So what does this mean? It means that my spring force is to the right. Okay, wait. Now, does this make sense? No. Why does it not make sense? Because try visualizing it. Imagine you take the load from here, right? You take the load from here, then you extend the load for 10 meters. What will happen to the spring? The spring will start bouncing back and forth. It will start bouncing back and forth to return to its original position. It will bounce back and forth to return to this equilibrium position. Now, if my force is to the right, it means my spring is going to keep extending until the end. Which doesn't make sense, right? It's not correct, right? Because the spring, the reason it bounces also, because it wants to restore to its equilibrium position. So, in other words, this F is actually known as restoring force. Okay, now this is, we did not include negative in our equation. Now let me show you what happens if you include negative in your equation. F equals to negative kx. So negative is there, k is 50, doesn't change of course, and x is 10. You will get negative 500 Newton. For my direction, negative means to the left. So, now, my force is to the left. Now, does this make sense? Yes, it makes sense. Because the spring is trying to restore to its equilibrium position. Where is your equilibrium? Your equilibrium is here, which is this line. So, it makes sense to say that your spring force or your restoring force is to the left. So that is why the negative is very significant. Now, does it work with compression as well? Okay, let's give it a try and see. F equals to negative kx. Okay, before we calculate, let's try to guess which side should your spring force be, or your restoring force be. Okay, so we're going to compress our spring this side. We're going to compress it. So try to visualize it in your mind. Where will the spring start moving and what will it start doing? It will start to restore to its equilibrium position. By what? It will start to bounce back and forth. It will keep bouncing back and forth until it reaches equilibrium and eventually stops, right? So where will your force be? Your force should be in this direction. So that means after we calculate, we should ideally get a positive restoring force to show that the restoring force is in this direction, directed towards the equilibrium position. So let's experiment it and see if we get positive. Okay. Our spring constant remains the same because I say regardless extension or compression, it doesn't affect your spring constant. So it is negative. Spring constant is 50. This is just an example of spring constant I'm giving. You can put any value and test it out. The theory will work. So 50. X is negative 10. Why negative? Because it's on the left side of your equilibrium. What will you get? You will get 500 Newton. And this is a positive value. So, it proves that our guessing is right. That yes, your spring force is directed towards the positive side, which is in this direction. Right. Okay. So that is why, in conclusion, why your negative here is very, very important. Okay. Now that we know about that, so what if, right? Okay, let's talk about something a bit different now. What if I want to know the motion of my spring? I want to know about the acceleration of my spring. What can I do? I can talk about net force. And we know net force has a formula F equals to ma. Now, if you're wondering where you saw this name F equals to ma, I hope you thought about my YouTube channel, because my YouTube channel is F equals to ma. But if you did not, and you thought about Newton's second law of motion, I'm still proud of you. Good job. Yes, you're on the right track. Okay, so coming back, F equals to ma. So what is F equals to ma? It's net force, basically the total force acting in a system. So let's look at the second scenario. Okay, so what is the total force here? We have spring force, which is the F equals to negative kx. F equals to negative kx here. Do we have the weight? Nope, we do not have the weight, because now we are looking in the component of x direction. We do not have the weight here. If let's say your spring is like this, then yes, you have your weight, you have your spring force. Spring force. But in this case, in the y direction, your weight is acting this way. There's nothing acting at this direction, but there is a spring force in this direction. Now in this case, we're actually ignoring air resistance. I know you might be thinking, oh, there might be air resistance or frictional force, anything. In this case, we are ignoring all that. So we just have our spring force. So what does this mean? Our total force, our net force, is actually our spring force. So Fs equals to negative kx, right? So we can write it as, you can equate the first one and the second one, because the total force is just negative kx, because we have no other force. So ma equals to negative kx. So I want to make my acceleration, my a, as the subject of the equation. So I write a equals to negative k over mx. So let's look at this equation for a bit and see what can we deduce from this. Okay, first thing, we have the thing I highlighted in orange here. This is actually a constant. Now why is it constant? Because k is a spring constant, which doesn't change, like I said, and your mass is also constant. Because there is no way when you extend, suddenly your mass would become 30 Newton or 30 kg. And then when you compress it, it becomes suddenly 10 kg. Doesn't make sense, right? It doesn't work like that, right? Okay, it's constant throughout, right? Okay, so your mass is constant. So with that being said, this entire thing is a constant. Therefore, we can say that acceleration is directly proportional to the displacement with the negative. This negative indicates that the acceleration is in the opposite direction of the displacement. Now, can we prove that from our diagrams? Of course we can. Okay, let's look back at scenario 2. Okay, let me erase all this. Okay, so based on our discussion earlier, we said that our spring force is acting in this direction. Am I right? And the only force we have in this scenario acting in the y component, ignoring air resistance, is the spring force. So therefore, our net force is a spring force. So that means our net force is also acting in the same direction. And we know F is equals to ma. That means your A is also acting in the same direction as the net force. So as you can see here, your displacement is acting to the right, while your acceleration is acting to the left. They are in the opposite direction. So this proves that acceleration is directly proportional to displacement and they are in the opposite direction. Okay. Yep. So does it work with compression as well? Of course it does. Our F net is this way because the only force we have is spring force. Therefore, our A acceleration also this way. Let's check and see. Our displacement is to the left. Our acceleration is to the right. And it is opposite. There you go. So, acceleration is directly proportional to x, just that it is in the opposite direction. So, actually, that is about it. That's the fundamental thing you need to know about simple harmonic motion, Hooke's law, the negative, and this equation. It's really very, very important. Yep. Actually, that is basically the definition of simple harmonic motion. It revolves around acceleration is directly proportional to displacement. And another thing to consider, speaking of definition, acceleration is always pointed towards the equilibrium. As I explained just now, because what will the spring try to do? It will try to restore to its equilibrium position, right? So it's always pointed towards the equilibrium position. You see your equilibrium position is here. You see where your acceleration is pointed? It's towards equilibrium position. Same thing here. Equilibrium position is here. Your acceleration is pointed towards the equilibrium position. Yeah, because why I mentioned this? Because it is also stated in the definition. So now that you understand how it works, you don't have to memorize your definition, right? Yep. So that's about it. That's about the fundamentals. I hope you get a clear understanding on why especially it's negative and how did we came about to this equation. So that's about it for today's video. Thank you for watching and I'll see you in the next video. Bye bye.